Hello world, my name is Nikita Black, welcome back to my channel. Today we will continue to improve our application by adding new features and by fixing what was already done. I noticed that my last video turned out to be very long. I want to avoid such long videos in the future. For me it's better to release shorter videos but more often, and because of this I'm stop talking. As usual, I'm wearing my Vulkan hat and jumping directly into my code editor. See you there. As last time, I want to start this video with corrections. In my last episode we changed the names of the folder for the third-party libraries. We changed from the source, if I remember correctly, to the version of the library. But this gitignore file isn't changed. It's a minor thing, but still nice to have. The problem is Visual Studio Code doesn't show any changes here, but in reality these folders they present, they simply not added to the Git source, and fixing this quite easy. All we need to do is just to ignore for this format library everything except this CMake file and the gitignore itself. So let's quickly fix that. After this change, we see immediately how Visual Studio Code changes its UI, so these things now grayed out, meaning they are ignored, and the status doesn't show the source for. As I recall, these dependencies are downloaded during configuration step of CMake, and it's not necessary to track them. So all the files now that have to be pushed to a Git repository to update it are these gitignore files. And another change is this try expected macro. This actually works, but it has some small annoying thing, and it relates only to this macro. This void version works perfectly, it doesn't need to be changed. But this try expected, let's see what happens when we have multiple calls in the same scope. Currently, how it works. We need to create some temporary variable or some field of a class, and this have to be provided here. This try expected will be expanded to this scope, and inside this scope the temporary variable will be created. Some checks are happening here, and the results will be assigned to this variable. As mentioned, it works, but what, for example, if I don't want to create this temporary variable, or what, for example, if I want to make it const? So this will not work, because here this complete expression will be moved here. Declarations of this variable will be moved inside this scope. That means that after the scope exits, we basically lost this variable. And also, what, for example, if I don't want to create it as a separate line, but I want to keep it here, like this. And this requires changes in this macro itself. So let me quick update this and then I explain how this works. So the signature remains the same, but now instead of doing this magic inside this try-expected macro function itself, it calls this helper, which is supposed to be private. That's why I added these two underscores here. So this macro now accepts the third parameter, which is unique variable, which is managed by this counter, because special C++ macro magic. So every time we call counter, it increments by 1. And this is necessary to create a unique temporary variable. Imagine if you have multiple calls, for example, A and B. Now we don't have a scope, so this variable is visible in outer scope. And if you just use some TMP variable, in this case it will be created twice, and we don't want to do this. In our setup with warnings as errors, the compiler will complain. Because of this, we need this helper to have unique names. After the very first call, we will have TMP0. It will do some check for this variable, and we expect that expression always return std expected. And we simply move the result of the expression to this variable. So if it's declared here in line, this complete expression will be replaced here, and this will work fine. And for example, if you have some class member or temporary variable, it also will work. So that's it. The reason I added two underscores after the concat is because this macro defined somewhere else. As you can see, it complains on redefinition. We could actually use this standard version, but it's so simple that it doesn't harm to have it as our own implementation. Now let me create a new branch for this episode and push these changes. Now let's plan the today's episode. Last time we ended by writing this step function, and we start to feel it today. We will not finish. I noticed that the last video became quite lengthy, more than 2 hours. I didn't expect this. I will try to make episodes shorter, and maybe we'll try to explain not so deeply, just to make things move forward. I'm thinking that I should not give this series the name Mesh Shaders, because it's more about introduction to Vulkan. Honestly, when we reach the Mesh Shaders themselves, it will be probably episode 20 or something like this. But yeah, let's think this is a clickbait. And in this episode, the plan is to create a logical device. Last time I explained the difference between physical and logical, and maybe some other stuff which we will need for our application. So here in this place we have the list of supported physical devices. Normally, if you have multiple devices, we can select one depending on something. Maybe we can save the previously selected one, or maybe we can add some launch parameter to allow to select the index of the GPU. But for now, let's just select the first physical device from the list of supported. On my machine, as you remember, I have two devices, the same device, in reality only one. I don't know how it will be on your machine. And the logical device itself requires some special preparation, but let's just pretend we have everything already in place. So at this point we do not have everything to create a device. We need a special structure, which I'll explain now. To create a device, we need to fill this device create info. And let's go from the bottom. You remember last time we spent quite a lot of time creating this abstraction for features. It was quite complicated, but I think it's necessary evil. And if you remember, we used physical device features number 2. So here it's 1, and the documentation explicitly says that this is legacy field, and it has a link to the explanation starting from Vulkan 1.1. If you want to use physical device features 2, they have to be provided in the pnext chain of the device create info. This pnext. So this thing we will ignore. These extensions we have already. We did some checks. Layers. Here it says it's legacy, not used. Before there was instance layers and device layers, I think, in Vulkan 1.0, but they removed the device layers, so we will ignore this too. These two fields. And this is quite a special thing, so this is more related to the hardware itself. So these queues, what they are. I like to think about these queues as pipes to our GPU. I had some idea to draw some very simplified GPU just to explain stuff more easily. Let me try to use this service, Draw. So last time I tried this, it didn't work in Firefox. Let me find how I can change the background color. I think it's here. So let's start with the GPU. So let this be our GPU. I would like to extend this picture in the future. Just show different kind of memories and different GPU related things. Let's start very simple. Right now we're talking about queues. And as I mentioned, I like to think about queues as pipes. So just imagine we have multiple pipes going into our GPU. And these pipes basically the ways for the data to enter the GPU from the CPU. They are needed to make things faster. For example, imagine we want to copy, let's say, 10 gigabytes of data, and at the same time we want to render something. So the way how we bring the commands to the GPU is through command buffers. We will see them when we reach this point. But just imagine a command to copy 10 gigabytes of data to the GPU, and the next command will be to render something. You can imagine that copying takes some time. Let's pretend it will be 1 second. During this 1 second, during the data copy, the GPU will not receive commands to draw something, so it will not basically do anything, will not draw. Just think about this as very simple explanation which relates only to our use cases. So GPUs can have multiple different queues. Let's give them a name, Q1, and Q2. Different GPUs can have different numbers, and they can serve different purposes, as we will see. Some queues, they are only for transfer operation. Transfer means copying the data. Some queues can be for compute commands, and other queues are for rendering commands. So let's pretend we use Q1 for draw operations, for draw commands, and Q2 for transfer operation. Now then we put the copy of 10 gigabytes of data to the second queue. Since they are separate, the first queue will send update commands without any delays, and when we create the device, we have to tell upfront to Vulkan how many queues we are going to use with this logical device. We won't do anything crazy in our application. We will use a single queue for everything, for graphic operations and for copying. We will not use any other operations, only these two, but we have to get the queue, and for this we need to fill this queue create info, and for this we need to get information about our GPU and how many queues and which types of queues it has. So the first step before creating a device is to get information about the supported queues. here we are working with queue families, not with queues directly, but with families. This should be queue family if we follow the Vulkan API. You have one family and you have multiple queues. You can specify priorities, as we can see, and runtime theoretically can somehow do something with this queues inside the family. But as mentioned, we will use a single queue family and the single queue. So the required queue count for a family is 1 in our case, and here we actually try to find the queue family. Let's see what exactly this function does. As a first step, we just get the number of queue families for the given physical device. This process should be already familiar to you. So in the second step, we are getting the queue family properties. This function returns void, as you can see. That means it should always be successful, so it can't fail theoretically. That's why it's not wrapped to some if-else. And then we get the queue families for our GPU. We iterate over this and check the queue count, how many queues the GPU supports for the given queue family. Again, in our case, the queue count is 1. I just added this parameter for the case we need more than 1, but I'm almost sure it will not be changed. And the second check is this queue graphics bit. As mentioned before, there are multiple queue types. Since we are going to render, we naturally interested in graphics queue, and this graphics queue is a bit special. You can see there are multiple different queues. The graphics queue is special because the graphics queue supports both compute and transfer operations. So when they create the graphics queue family, we can call compute commands and transfer command. That's why we need only one. We will not use compute operations, as I mentioned before, but of course we need to transfer some data, copy some buffers, for example, and we need transfer operations. So that's why the graphics queue will work for both operations. Also, we need to check that for this device, this given queue family supports presenting. Presenting means that the GPU sends some data to your monitor to render something, and this, as it turns out, is a special operation. And theoretically, you can have a graphics queue which does not support presenting. In this case, we need to create other queue, and we need to manage multiple queues. I will not do this in our application. Honestly, I never saw any GPU with graphics queue which does not support presenting, so it's very unlikely that you will see this also. But if you want to strictly follow the rules, after this loop you need to check if the graphics queue and the present queue are they the same or not. If they are different, then you need to add some special code in some places during submitting synchronization, which is quite complex and very confusing. We expect that our single graphics queue supports presenting as well. If not, then it's error and we can't proceed. But it's fixable. If your GPU is special and has this kind of stuff, you need to find a solution. Now you know at least what to search for. And to get if the queue supports presentation or not, we are using this function, this Vulkan call, where we provide the device, the family, the surface, which we got in the last episode, and this is the return result. And as soon as we find the first queue which satisfies all our requirements, we return this family. So the family queue is just uint32. Let's check if it compiles, and let's see how many families and how these families look like on my machine. I have 6 different queue families. Here I didn't mention I need to specify this S type, because if I provide the queue families data without the S type, it crashes, if I remember correctly. So that's why I have to use this. Actually, let's see what happens when I don't do this. No, it not crashes, but if you look at the queue families, this structure is correct, but this S type shows completely different stuff. I don't know, maybe they fixed this, maybe I'm just wrong, but if I remember correctly, previously I had some problems if I do not specify this. So let's bring it back. Let's stop and recompile. And let's see what these families look like. So 6 queue families, for example 16 queues. We need maybe to decipher this to figure out what this looks like. Or we can use the already familiar tool Vulkan info with the first GPU. So here the information, and here we can see our family properties. There should be 6. 1, 2, 3, 4, 5, 6. Yeah, that's right. The first family supports up to 16 queues, and it supports this operation: graphics, compute, transfer, and sparse binding. The second queue only supports 2 queues and transfer. That means that we can copy at the same time 2 different streams, for example, and at the same time we can record and render something on the screen, and everything will work in parallel. As you can see, so this transfer bit, it supports only a transfer and this binding operation. The compute supports both compute and transfer. As you remember, graphics supports compute and transfer. Compute supports compute and transfer operation. Transfer supports only transfer. We also have one more transfer, but this is probably only for video decode, and this is quite a special thing. Yeah, that's it about queue families. So we will use obviously only one queue from this family. Let's delete this, and after this call we have queue family. This should be 0. Let's check it one more time. Graphics queue family 0. Okay, it works. And with this we can implement this create device function. It requires physical device, our family, and the number of queues. That's why I created this variable. So now let's implement this create device function. Okay, done. So inside this create device function, first we need to create this device queueCreateInfo, because this is what the device createInfo expects. So this queueCreateInfo takes the queue family, which we have, the number of queues, which is 1, and the priorities. This is necessary. The number of priorities should be equal to the number of queues. Again, theoretically, you can have multiple queues. As you saw in my case, it can be up to 16 queues, and some queues can have different priorities. I don't know how it works and if it's supported at all, but I could imagine some implementation do something special and just update different queues with priorities more often. I'm using this std_fill algorithm because although we use queue count 1, I still added this as a parameter, and in my case I fill all priorities as 1, but you can play with this and you can use different queues, and you need to replace this call to different function which will create different queues. The next thing, we need required extensions, and you remember we did this last time, and I created this as a layer of abstraction just to not to repeat it multiple times. And here the device createInfo expects this to be char pointers, but our extensions are std string, and here I convert them to pointers. Since this alive on the stack, it's perfectly fine to just take the pointers to strings and use it here. So after this call, we are not using all this anymore, and it's safe to use it here. Another interesting stuff is this features we did last time, and you remember almost all functions in these required features were static, all but this get chain. And I promised to show why, and this is exactly the place. We need to provide these features and the chain of different feature families as a pnext, as you remember, as we saw here. If you are using features, we need to provide them as a pnext. And as you remember, this chain is a chain of pointers, and all this separate structure which point one to another have to be alive somewhere until this function exits. That's why we have to create this variable on stack, and that's why it's not static. That's how we ensure that no segfaults happening. Documentation says these are legacy, but still I just fill it with empty values. So our extensions and these features have to be null because we're using them here, and here we just call the usual create something Vulkan function. Let's compile it. Let's try to run it to see that it works. It works. Cool. And now when we have instance on device, we are basically free to do everything. With Vulkan, these two objects are enough to create anything else in the API. And today we will add the very special thing, the so-called Swapchain. The Swapchain is just the collection of images where our application is going to render into. Let's for a second imagine that we do not have something like Swapchain and we want to present an image in a window. Let's say we created a window, something like this one, and we want to fill it with some 3D graphics or just to clear the color. How you would normally do this? You could imagine that you as the developer create an image, a special Vulkan object, you render into this image, or maybe you heard the word frame buffer, and then you just tell, okay, Vulkan, please take this image and present it on the screen. And since Vulkan is a very low-level API, it's actually expected to present like this, but you can imagine that to present something, the image and the presentation engine, which is operating system-based functionality, is expecting images in certain format. For example, they have to be allocated in some place, they have to have a special format, RGB or BGR. It should have a specific size, it should have different requirements, the operating system should know how to work with it. Also, you need multiple images, because if you have a monitor with 60 Hz refresh rate, that means that image is presented on the screen for 1/16th of a second. And during this time, during this 1/16th of a second, you're not allowed to draw anything because the image is presented currently. So that means that you need to have multiple images, while one image on the screen, you draw to another image. That's what makes Swapchain very special, because again, it's a mix of everything. It's a CPU, it's a GPU, it's operating system, it's absolutely not cross-platform. And in Vulkan, we create Swapchain by filling this structure. As you can see, it have a lot of fields. Some of the fields are already known. For example, we have a surface, so we have, what else? Actually, we don't have anything else. And we still need to figure out how to find the unknown fields. If you look at the names, this KHR means operating system dependent, and it's implemented differently for different platforms. We will start slowly by creating the skeleton function first, and then we will see what we need exactly to make Swapchain happen. That's it. That's the base function with question marks instead of unknown values. Let's quickly go through and see what does what. The surface, we have this. The image count, that's simply the number of images in the swap chain. The operating system will try to change the images between rendering in some order. The order is not specified. And here, as you can see, it doesn't say the exact image count, but it says minimum image count. That means that if you specify here number, let's say 3, it will be minimum image count. The engine, the Vulkan operating system can create more than 3. It's possible. The image format, as mentioned, you can't just set any image format you want. So it have to be very specific value, and we have to request it before creating swap chain. The same goes for image color space. The extent is the size. of an image, and it depends on the window size. For example, we can resize it, change it, and every time when we resize the window, we need to destroy the previously created swap chain and create a new one and specify the size here. I think if we decrease the size, it's not necessarily to destroy, we can reuse just a smaller portion, but we will do the simple way, so every time the size changes, we recreate everything. Thankfully, that's not very common operation, so it doesn't happen very often because it's quite heavy. Number image array layers, we use one. You need more than one when you have multi-view swap chains. VR screen, for example, has 2 screens, but we are doing normal desktop application. The image usage, we are going to render to Swapchain image, and we will use this image where we're going to render into as a color attachment. I actually can't even imagine when you use another bit for Swapchain image. So we use this value, the sharing mode. We will see this multiple times for different kind of resources. It basically says that if you are using multiple queues, how this object have to behave. We won't use multiple queues, as you remember, we have a single one, and here we're saying that we will use the object every time in one queue, so we will not share it between different queues. These two fields relate to queues again, which you have here concurrent, then you have to fill this values here. Pre-transform. This thing is used, then the surface can be rotated. For example, if you have a tablet, you can rotate it and the rotation changes, and for this you need to specify different kind of transforms. Honestly, I never used this because I didn't write Vulkan code for tablets. For desktop, it's theoretically possible to rotate a monitor and something should happen. Again, I didn't do this. So we will use the variable which comes with some other data. We'll see this in a moment. Composite alpha, that's how the image will be presented in operating system. For example, here we have a pack window, but we can have a transparent window. For example, you have multiple windows overlapping each other, and if they have a transparency, this should be announced to operating system before you create the swap chain. We won't use any transparency, so that's why it's always a pack. The present mode, again, very special thing. You probably heard about vsync, and that's exactly what it is. How the images are presented on the screen. Should it wait for the vertical blank of the monitor, or should it be presented immediately when available? There are more than 2 different modes. We'll see this. Clipped, it tells that the pixels outside of the visible area can be discarded, and the old swap chain, somehow it can be used to create a new one. Maybe some information just copied from the old one, so it need to be passed here. Then with this data field we pass it to create swap chain function, and finally if the old swap chain was passed to this function, we destroy it because we don't obviously need the old swap chain. And if you have multiple full resolution images in the swap chain, it takes quite a lot of memory. Now let's go step by step for each individual unknowns and see how we can get them.
In the first step here, I'm trying to get the surface format for this selected physical device for this created surface. Let's look inside what happens. So here I'm using device info number 2. That's not necessary here, but yeah, I prefer just to use the latest versions of everything. First we get the number of formats, and second we get the formats themselves. And this is very special thing what this check does. For all formats supported for this combination, I specifically look for nonlinear sRGB surface and sRGB format. Why this is important? It's important because, of course, you heard probably about gamma correction and that your monitor is nonlinear, meaning that if you specify, for example, color value 0.5, it will not be in the middle between 0 and 1. It will be slightly more darker or brighter, I don't remember actually. But this sRGB things means that in the shader, when we read from an sRGB data format or write to an sRGB format, we can specify linear numbers and they will be converted automatically by the driver, GPU, Vulkan, I don't know how actually it converts them. In sRGB color space, we want to always work with sRGB formats. So besides this color space, there are multiple other exist, but for me they look very esoteric, I would say, because I honestly have no idea what this means. Let's hope that this surface will work for your machine, because I never saw any device which doesn't support this format. There are multiple sRGBs formats, but the main thing here is sRGB. There can be, for example, unorm format or uint, sint. In this case, if you take sRGB color space, but for example this uint, something weird can happen, so no automatic color conversion will happen and we will see washed out colors on the screen. Yeah, and why here BGRA and RGB? I remember that in my setup on 2 different machines, on Windows and on Linux, I had a different combination. We will see in a moment. Actually, we will see it now. Then I put a breakpoint here. Compile it once again and run, and we will see how many formats I have on my machine supported. Here I have only 2. BGRA with sRGB nonlinear space. So okay, I have sRGB color space, but with 2 different formats, sRGB and unorm. And that's exactly, if I would select unorm, then I will see the wrong colors when I write in shader a linear value, for example. The code will work in any case. For example, if this check will not fire, the runtime will hit this point and will return the first format. In my case it will be this one, incorrect, but it's guaranteed by specification that one format exists. Okay, that's done. The next thing I would like to do is to find the present mode. I will skip these 2 for now and get this thing. here is how we get present mode. So as usual, the number of present modes and then the modes themselves. And here I check that this present mode is supported by my hardware, and if it is, I just return it. If not, then I return this one, which is guaranteed to be supported. If you don't believe me, you can see it here. Present mode FIFO. This is the only mode which is required to be supported. So what's the difference? These two modes, they are basically VSync enabled, meaning there will be no tearing, and also the maximum refresh rate will be tied to the display refresh rate, so you can't get faster. This FIFO mode, it holds internal queue. If your GPU renders very fast, faster than you can present, then these frames will be queued. Let's say we have 3 frames for our swap chain. One is presented, and if you do it very fast, we can queue 2 more frames. That means that after 1/16th of a second, if we have 60 Hz monitor, the first one in this queue will be rendered, and after another 1/16th of a second, another image. The second image will be rendered. That's not bad, but this could theoretically introduce some lag. You can show an image which is already outdated. With Mailbox, there is a queue, but with only 1 slot. So if you render too fast, faster than the presentation, if you put some image, for example, a frame there, and if you render and present another frame, if the previous frame still is in the queue, it will be replaced by the second frame. That means that you will always show the most recent frame. That means, for example, the input lag will not be so noticeable. Yeah, but this thing is not guaranteed to be supported, that's why it have to be requested. Now let's see how many modes and which modes I have on my machine. I run it in a debug mode. That's still the old debug point. So I have 4 present modes. This is guaranteed to be supported, relaxed, immediate, and these 2. Okay, so I do not have Mailbox at all. This immediate mode is VSync off, meaning you can have a tearing, which I don't want, but I maybe introduce it, I don't know. Anyway, this I don't remember and don't know what is it, and this one requires a special feature to be enabled, which I don't want to enable as well. For our simple application, this one is fine.
Let me quickly put the present mode here. And let's think what to do next. For extend, we need to know the size of the image. For transform, we need to know the capabilities. And for the image count, here I'm using the fixed image count, but that's not guaranteed to be supported, that's Vulkan. Before requesting the number of images, we need to be sure how many images can be supported at all. And for this, we need to know the surface capabilities. And this is the next function I will create.
Okay, so this function is very straightforward. There is nothing happens here. We fill info, we prepare capabilities, and we just call this function, and after this we have these caps with these fields filled. Here in Swapchain, I'm using these capabilities to get the current transform. As mentioned, for desktop application, this will never change. You just need to copy this line. And also, the surface capabilities has the supported number of images for the Swapchain. And this have to be considered here. So let me add this line. Okay, so in these lines I just compare the requested number of images for the Swapchain with what is supported. And now the only thing left is the image extent. As mentioned, every time we resize the window or create the Swapchain the first time, this value will be different. This will be acquired before creating Swapchains. Let's create another function to get the size of the Swapchain. Inside the function, we need to handle two cases. The first case, where the system tells us the size of the surface. We have to obey this and use whatever it says. In the second case, then this value has a special meaning, and this is indicated in the specification. The current extent indicates surface or a special value. In this case, we need to choose the size by ourselves. And as usual, we can't just take a random number and hope it will work. We need to check the possibilities of our hardware. This is where I select the width and height depending on the minimum and maximum possible sizes. After this, I pass this extent to this function. Let's maybe put a breakpoint here and let's look what surface capabilities are on my machine. But before, I need to create a swap chain. Let's compile it. It compiles, and now when we try to run it, let's look what happens. So it crashes, and it tells us exactly why. This function is null, doesn't exist, and here it asks, did we enable the extension? And we did not. So
to create the swap chain, we first need to add the extension to enable this. This is a device extension, and we can find this in the specification. For the swap chain extension, it tells that's a device one, and that should be pretty easy. All we need to do is to add it here. This is KHR extension, and after this line we should be able to run it. And now let's do it one more time with the debugger to see what we wanted to see, the capabilities. Here they are, surface capabilities, and here it tells us on my machine the minimum number of images is 3. Here, if I want to create double buffering with 2 images, it will not work because 3 is the minimum, 8 maximum, and it tells us the current extent, these numbers. Also, it has minimum and maximum, they are the same. So the first time when we create swap chain, we have to use this width and height. This is the current transform, so this works. Another interesting thing, let's run it one more time. Here we see the out saying that we are creating the swap chain, but if I try to resize, nothing happens, and that's pretty obvious because I never handle the resizing. Here we create the swap chain when we initialize the graphics manager. The next logical step would be to get this functionality and move to resize function and call this resize when we resize our window. Let's do it now. This is how the resizing works. So I created the resize function and moved the swap chain related code here. First time we call this function when we initialize the graphics manager, or for example when we change the device. And also I introduced this start frame function. Inside this start frame function we trying to get the window size, and if you remember, the window size function tracks the state of the window and returns the boolean saying if the window was changed or not since the last call to the size. Inside the graphics manager I checked this field, and if it says that the window was resized, we call this resize function again. Now inside the main, inside our update loop, I call this start frame. It will grow with time, so we add much more stuff here, but for now it's very simple. And basically this is how this works. Every iteration we check if the window was resized. If it was, we call the resize. Now, if you run the application, just look at the log message, we can see that it tells us something is resized, something was created. Cool, it works. We created the swap chain, but we didn't finish with the swap chain stuff. We need to do a couple of things more. But before we proceed, I want to introduce the very important topic I didn't touch till now. It's cleaning of our application, of our state. You can see that inside the graphics manager we are creating a lot of objects, but we never destroy them. Actually, that's not a big deal, because when we close the application, the operating system and drivers will do it for us, but it's just a good habit to do this, and especially if you want to change physical device on the fly, we want to clean everything before creating the new objects. Let's introduce this new destroy function and add the cleanup code there. Destroying objects in Vulkan pretty straightforward. For every vk create function, there is a corresponding vk destroy function where we provide the object to destroy, and the allocation callback. We always use null pointer, so we use null pointer here as well. I split the destroy in two parts. The first is destroy device, which is called when we change a device. This is the private function, and the public function, which we call in the main when we finished with everything, when the main loop is exited. We call the graphics manager destroy, and it destroys the device, instance, and other things. Here I deliberately omitted the Swapchain and surface destruction because I wanted to show one thing. Now, if we run our application and close it, everything is fine, it doesn't say anything. But if we launch our Vulkan configurator, and we need this for validation. You can introduce validation with different ways. You can use code-based validation, you can use environment variables, but this is the simplest way, using the Vulkan configurator. Then you start the application, it automatically adds the validation to your application. You can select some specific Vulkan application or any as here, and this validation, just the basic validation, checks a lot of stuff, for example object lifetime. Now with this validation layers enabled, if we run the same application, we see some errors. So it tells that we need to enable this extension. We are using this function, but we didn't enable the extension. And the second thing, if I close this, it tells that the Swapchain surface has not been destroyed. Here I wanted to show the importance of layers. Even if application seems to run okay, it doesn't matter that it's correct. And here we have a couple of errors. Our goal is to always have zero this kind of warnings. Now let's fix this. Object destroying pretty easy, so we added a new function, destroy surface, destroy Swapchain, and for the extension, we added this required extension, which is instance extension, by the way. Here, the validation layer explicitly tells us what needs to be added. Now let's compile it. Now let's run it again. We see 0 warnings when we resize, and then we close, no warnings. So our application perfectly valid, and congratulations with this. Now let's go back to our Swapchain. Once again, Swapchain is just a collection of images which is managed by operating system, let's call it like this. But usually in Vulkan we don't work with Swapchain as a wall. Instead, we usually work with separate images. For example, when we want to render to the first image of the Swapchain, we need to know this image as a Vulkan object. Normally, when we create objects like images or buffers by ourselves, we go through a very long and complicated procedure of allocating memory, specifying parameters. But in case with the Swapchain, we just receive it, ready to use, but we need to obtain the images. It's very easy. We don't need to work with memory directly. All we need to do is to get the images out of this Swapchain. That's the first part. The second part, in Vulkan, it's very unusual to work with images directly. Instead, you work with image views. You can think about views as a specific window to an image. Maybe it's very hard to explain. If you imagine some non-single image instance, for example, MIP map in Vulkan, a complete MIP map chain is a single image, but then you work with it. For example, if you want to read from it or write to it, you need a small portion of this image, and you look at this as a small window, another view. Another example would be arrays of images. You have an image, but it have multiple layers. Still, in Vulkan, it's a single image, but then you work with it. You usually do it through views. There are many other examples, but that was just clarification why we need another step over images. So here we need this as well. When we work with Swapchain, there are images, physically baked memory, and the views which look at a specific resource somehow specifically. These two steps we will do today. We get images and we get image views for the Swapchain. Let's do it now. That's it. These functions luckily very easy to get Swapchain. First we get the number of images inside Swapchain, then they allocate the necessary amount of memory and just get these images. As mentioned before, we don't manage this memory. Vulkan just gives us whatever it creates with all the necessary formats and alignments and everything, and we just use it. And here is how we create image view. Oh, that's a bug here. Here I provided this type as image create info, but it should be image view create info. It's very hard to debug. I believe if we just run it, it will crash with some strange errors, segfaults maybe, so you should be careful. To create an image view, we need of course an image, and we need to specify other data. For example, the view type, we will work only with 2D images. The format, we get this format when we wanted to create Swapchain. The thing is, you can have an image with certain format, but you can read it, you can view at this image with some other formats. Not any formats are compatible, but there is a range of formats which are compatible, and you can look at one format and automatically convert, then you read it. But in our case, we will use whatever we created Swapchain with components. We can swizzle different components. If you want to sample an image and read a single pixel, it will return an RGBA data. And if you specify here something different, for example, if instead of identity we specify 1, 0, when we read this pixel for this image, for this view, we will get 1 or 0, or we can just redefine, and instead of red, it will return as green, and we can even turn the colored image to grayscale if we specify here everything as red, for example, which we won't do. And the range is about the view itself. Here we specify the MIP level, the number of MIP levels in our image, and the number of layers if we are using image array. Again, the Swapchain creates 2D images with a single MIP level, with a single layer, so as specified here, and we are using the index 0 for both. Then we run over images, and for each image we create a corresponding image view. That's it. And we want to get the images as soon as we created Swapchain, and we want to create image view as soon as we get images. But the thing is, here we have the word create, here the word get. Get usually means we don't manage something, we just obtain, and so we don't need to destroy this. But if we created something, we need to destroy. Here, before creating Swapchain, we destroy the old image views if they exist, and we do the same when we clear our device. But again, we don't need to destroy images because we don't manage them. Swapchain manages, and when we destroy Swapchain, the memory will be destroyed. Let's compile it. I have configurator running. Now let's run it. I don't see any validation errors. When I resize, we can see that we get in Swapchain images, creating Swapchain image views. When we close, I do not see any warnings also, which is fine. But for example, if I comment this thing and run it again, I resize multiple times. Now then I close the application, it should show many warnings about undestroyed image views. That means that everything works correctly. That should be it for today. I don't want this video to be very long. Let me commit everything for this part, and I don't know what actually to do for the next episode. We will figure out next time, so please stay tuned and take care. See ya!